wanted to prove that intervals in R are connected sets, and then we will also prove that they are the only connected sets in R. So, we started by proving this by contradiction. Suppose there exist non-empty closed sets in X. So, we are considering capital X as a subspace of R. So, when you say that X is connected, mean the tau topology on R, then tau restricted to X. So, X with respect to this topological space is a connected topological space. That is what we will have to prove. Suppose there exists non-empty closed sets, say A comma B in X, such that they are disjoint and X equal to A union B, that is it has a separation. Because X is non-empty, we have taken an element X in A and Z in B, and we have assumed that X is less than Z. Then we considered the set closed interval X Z intersection A. This is a X is here, X is in A as well as here. So, this is a non-empty set and Z is an upper bound. Now, this is a non-empty subset of R which has an upper bound, hence least upper bound exists, we have denoted that by Y. So, that is supremum or least upper bound of the set. So, set of all A such that A belongs to closed interval X Z intersection A. That Y is a real number. Then our aim is to prove that prove that Y is in Y belongs to A as well as in B, and that will give us a contradiction. So, that is you want to prove that Y is in A, that is enough to prove that Y is in the closure of A, that is to prove Y belongs to A closure with respect to X, that is in our subspace X, and A is, we assume that A closed in X. So, that means A closure with respect to X will be equal to A. So, enough to prove Y is in the closure with respect to X, and similarly we will prove that Y is also in B. So, for that essentially we will have to take an open set in our subspace containing Y. So, enough to consider basic open set, that is how we can started with. So, let epsilon greater than 0 be any number. So, now in fact that is what essentially we will consider the open interval Y minus epsilon, Y plus epsilon. This is a basic open set in R, then intersection with X will be a basic open set in X. So, we started with epsilon greater than 0. Now, Y is already a least upper bound. So, now Y is in fact is supremum is unique for us. Y is the supremum of closed interval x z intersection A imply y minus epsilon, that is this is the y is the least upper bound. So, y minus epsilon is not on, just write upper bound, not on upper bound for closed interval x z intersection A. So, now it is not on upper bound means what? Hence, this implies there exists at least one element, say x, there exists an element x naught in x z intersection A such that element, that is this y naught minus epsilon is less than x naught. So, that is we have our supremum y, and of course, we can assume that epsilon is such that the distance, minimum distance between x and y, epsilon is strictly less than, assume that epsilon is less than distance between x and y, and epsilon is less than distance between y and z. So, that is, so this is our y minus epsilon. So, y plus epsilon, mean y plus epsilon less than z provided y not equal to z. So, in that case we are interested. So, here now we got an element y naught minus epsilon is less than x naught. So, x naught is, because x naught is in our closed interval x comma z intersection A, x naught will be less than or equal to y, because that is an upper bound. So, x naught is here. So, that will imply this give us x naught belongs to, this implies this x naught already it belongs to A here. Now, by we got there exists an element x naught in A, also it is in x z. So, that is x naught belongs to A intersection x z is such that our started open interval, that is y minus epsilon y plus epsilon. So, x naught belongs to this interval y minus epsilon to y plus epsilon. In fact, that intersection with our x, this is a open basic open set containing y in x, that intersection with A, but A is subset of x. So, that means this y minus epsilon y plus epsilon intersection A. So, this set is non-empty. So, x naught is in y minus epsilon y plus epsilon, also it is in A. So, that is this is non-empty, since our say that x naught belongs to this set. So, hence for each basic open set of the type open interval that is each basic open set x naught minus epsilon, x naught plus epsilon, intersection x. This is a basic open set in X, that intersection with A is non-empty. So, that implies, pardon, yeah, open interval x naught minus epsilon, x naught plus epsilon. Yeah, sorry, the notation is, yeah, we wanted that. Right. So, that is to prove that we wanted y is in A, that is we started with, yeah, here the y minus epsilon, y plus epsilon intersection x, intersection A is non-empty. That is what we have proved. That imply this y belongs to closure. So, meaning is either it may be, if y is already in A, there is nothing to prove, or it should be a limit point. So, that means in general we want to prove some element of the given topological space in the closure, mean for each basic open set U containing Y, U intersection A should be non-empty. So, that we have proved. Exactly the same way we can prove that this Z is also in, Z is in B. So, this I will leave it exercise. Yeah, similarly prove that Y is in B closure with respect to X, which is A, because A is a closed set. Similarly, Y belongs to B closure with respect to X, which is in B. So, that is, this will imply Y belongs to A intersection B. So, that gives a contradiction. The proof is exactly similar. If we take a neighborhood containing this right side. So, this right side already, if y equal to, say here. So, y equal to z, there is nothing to prove, because already z is in B. So, otherwise y is strictly less than z mean. So, we can find epsilon small enough, then this right hand side we can find an element which is in the neighborhood, and also it is in our, I mean, open interval y minus epsilon, y plus epsilon intersection B. So, that will give that y is in the A intersection B. So, hence what we have proved is every interval in R is connected. So, in any, whether it may be a open interval, open A, open infinity, or closed A, open infinity, or closed interval A comma B, any type, open A closed B, closed A open B, all these are all connected sets, connected subsets of R, mean any interval, including, interval mean including singleton x comma x, that represents singleton x, open interval x comma x means that is empty. These are all also connected subsets of R. Now, it is easy to see that in fact these are the only connected subsets of R, that is, suppose the given x is not an interval, that means including it is non-empty, not a singleton, and not an interval. So, suppose x is not an interval and it contain at least two elements, and x y it contain at least two elements, yeah, x is not an interval. Now, what is the, now capital X is not on interval implies there exists x y belongs to our space X, and it is not an interval mean there exists x in capital X, y in capital X, and a point z say that x less than z less than y, but z is not in X. So, x is in X, y is in X, but there is a point between x and y, say that z is not in X. See, now it is just easy to see that consider the open interval minus infinity to open Z. So, that is an open set in R, then we can restrict that to X. So, then that is a open set containing the point X. So, again we have assumed that X is less than Y. So, consider the set A as open interval minus infinity to open Z. This is the open set in R. Now, intersection with X, this is open in X. In fact, it is a basic open set, and X is in capital X, and also X is less than Z, hence X is in A. So, that is A is a non-empty open set in X, and also capital B. So, now consider from the other side open Z to infinity. So, open interval Z to infinity is an open set in R, hence now we are going to restrict that open set to X, that means intersect with X. This is a open set in X, and Z less than Y less than infinity, I mean it. So, this will imply this Y will belongs to B, that means Y is a belongs to B, hence B is a non-empty open set in X. So, we got that is there exists, that is hence there exists non-empty open sets capital A comma B in X, say that 1 they are disjoint. See, in fact, the only here minus infinity to Z, all the points here in A are less than Z, whereas here greater than Z. So, A intersection B is empty, and A union B. So, we are restricting already, they are subsets of X. So, that will be equal to the whole space X. In fact, it is like the only element which is here in this set minus infinity to Z union Z to infinity is Z. So, that Z is not in our X. So, this union will give us the whole space X, hence this will form a separation for X. So, this will imply X is disconnected or say not connected, X is not a connected set. That means, if it is not an interval, then that set is not connected. So, we have proved that intervals are connected sets, and they are the only connected sets in R. So, now this is a very important result for connectedness. See, now we will see that See, for example, take even a closed interval 0 1 and take a even a curve with the initial point curve in R2. So, it may be a curve. So, like this, starting from a point A, initial point A in R2 and some end point like this. Then in fact, we will see that this closed interval 0 1 is connected, will imply even a curve like this is also a connected set in R2. So, similarly even including if we take open interval, so it may be a curve like this, these are all connected sets. So, for that what we need is, we will prove that image of a continuous under continuous function, continuous image of a connected set is connected. So, we will prove this as a theorem. So, we have let x tau, a topological space x tau, y tau prime be topological spaces, and f from x tau to y tau prime is continuous. Will assume without loss of generality it is onto, that is essentially you want to prove that the image, that means image of x is f of x. So, our topology instead of y, if it is not onto, what we want is consider y equal to f x, then restrict the topology tau to f x. So, we have to, if it is not onto, in place of y consider f x and consider the topology tau prime on y and restrict that topology to the range. So, we want to prove that this topological space f x is connected. So, that is why if it is on to mean f x equal to y. So, and this function x y topological space and f from x on to y a continuous function, and this be a continuous function. Further, suppose x is connected. Further, suppose our domain x tau is a connected topological space. If then y with tau prime is also a connected topological space, or simply we say that connected space. That is what we say, that continuous image of a connected space is connected, and this has many applications. So, now if we know that one set is connected, so that is what immediately we are going to see that. See, if we have we know that the real line R itself, open interval minus infinity to plus infinity, and interval, this is connected. Now, fix any element in the plane R2. So, take a point. So, fix that point, let us call order pair A comma B belongs to R2, that is fixed. Now, take a line passing through this point parallel to x axis. So, this and in fact there is topologically, that is what we will feel that there is no difference between these two lines. So, if we take a point here, just draw this vertical, this is for say x, this is the image, or you define a map from x belongs to or the corresponding point, let us say f x is in this set, say this is R, this let us call R prime. So, then in fact this will be a translation. So, this map, if we have point y here, this is over f of y. So, this is a continuous map. In fact, here this such a map is nice map in the sense that f is bijective, f is bijective, f is continuous, and f inverse is also continuous. Such a map we call it a homeomorphism. So, that means essentially if you take a basic open set here, mean it is an interval like this. So, the image also again a interval in this line. So, this will be a homeomorphism for us. What is in f is continuous. This function f is continuous and f of R, the image is R prime, it is onto also. So, R is connected imply this line is connected. So, not only this and any, that is why we have seen that if you take a curve, we can find a continuous function from some interval to some interval. In fact, we can prove that there is a continuous function from, if it is a open, the endpoints are not there, from the open interval to this arc there is a continuous function, then that will be a is also connected. Yeah, now quickly we will see that there are many sets using the given some collection of sets which are connected, then using that we will see that how the union is connected, and the if you have a set A, I mean set A mean a subset of a topological space X. See, a subset is A subset of X and this set is connected. That means as a subspace A, tau topology on X, tau restricted to A, topology on A, this topological space is connected. Then we will prove that the closure is also connected. And similarly, if you have a collection of connected sets, see essentially you have, now we have seen that if there is a interval, for example you take the open interval, take even minus infinity to 0 or even say open interval 1 comma 2, and this is our A, capital B, A is open interval 1 comma 2, B open interval say 2 comma 3, X equal to A union B. So, then this is not connected, but if you see that is what, but A is here, we will see that A is open interval 1 comma 2 is connected. Then if we take the closure, that closure in this case it will be closed interval 1 comma 2. So, that will be connected. I mean if you add not only this, from the set A we can add some additional elements of the given topological space, they are from suppose a set F, F subset of all the limit points of A, then we will prove that A union F is also connected. That means from a connected set if you add either all the limit points or some of the limit points, the new set will remain connected. So, for that we will not prove all the results, we will give the main idea and we will leave the rest for exercise. That is, so this observation is very important, that is, given Y a subset, we can assume that non-empty, a subset of a topological space X, then what is a separation for Y? So, a separation for Y. So, what do you mean by a separation for Y? So, suppose there exists non-empty subsets capital A, capital B, non-empty subsets of capital Y such that 1 they are disjoint, A intersection B. Yeah, see here not just disjoint, we will assume that A intersection closure of that B, here the closure with respect to the given topological space X. So, something more than stronger than disjoint, and A closure intersection B is empty, that is first condition. Second, Y equal to A union B. Then we say that Y has a separation because they are all non-empty subsets. Note that we have not told that they are non-empty open sets or closed sets, they are just non-empty sets satisfying this condition. Then this will imply we can prove that Y is not connected. That means Y is connected if and only if there cannot exist separation of this type. So, that means what is enough to prove is, suppose Y has a separation, imply, that is, note, if Y admits a separation, imply Y is disconnected, that means not connected. So, that is what is enough to prove is the same set A, already they are non-empty, just it is enough to, and Y equal to A union B, enough to prove that A is closed in Y. Similarly, capital B, same proof, because these are all symmetric, enough to prove either A is closed or B, the remaining second part will be similar. So, enough to prove that A is closed means the closure with respect to Y equal to A, that is what you have to prove. So, by definition what do you mean by now? What is the closure with respect to Y is same as closure with respect to the whole space intersection Y. You just you restrict the, this is easy to verify, and Y equal to A union B. So, which is equal to A closure intersection Y, which is same as A union B. Now, this distributive law, so this is same as A closure intersection A union A closure intersection B, but given that A closure intersection B is empty. So, hence A closer with respect to y is same as, hence the closer with respect to y is same as this set is empty. So, this is same as, again A is subset of A closer, hence it is A, that is A closer with respect to y is same as A. This implies A is closed in y. So, similarly we can prove that the set B is closed, and hence if we have a separation in this sense, y has a separation like this, then that will imply the set we have a separation for y in the usual sense, that means using our definitions, that in other words this A is a closed set in y, B closed set in y, B equal to A complement. So, that means, so we have a subset which is both open and closed, which is non-empty not equal to x, that will imply it is disconnected. So, this will imply y is disconnected. So, now if we use this result, I mean as a corollary, I mean not as a corollary. So, if we use this result, we can prove that suppose you are given y connected, x has a, x need not be connected, and x equal to A union B, and this is a separation, that means x has a separation and y is subset of x is given, y connected, and this is such that either A non-empty, B non-empty, either this condition or A and B both are open set in X. Then this will imply y is completely contained in A or completely contained in B. See, geometrically it is easy to see that. So, we have a separation for X beam, this is like our A, this set is B, the union is the whole space X. So, now y is, suppose y has some part in A, so that means some part of y, so let us say y is in A, that means y restricted to A, this set is also non-empty, and some part from B. So, that means y intersection B, this is also, this portion is non-empty, this is non-empty. So, then this will implies what, y will be equal to y intersection A union y intersection B. So, they are non-empty, y intersection A non-empty, y intersection B non-empty, A, this is A is open if it is in X, because it is a separation, A and B are open set, then this will be open in Y, open in Y, similarly this set is open in Y and Y equal to this. So, hence that will form a separation. So, one of the sets should be empty, that will imply Y should be contained in either one of them is empty, means suppose A is empty, then this set will be B. So, Y will be contained in B. So, using this idea, now if we using this, we can prove that exercise. Suppose you have X topological space, y1, y2 connected subset of capital X such that the intersection is non-empty. See that, so then this will imply the union is connected. In general, y1 connected, y2 connected need not imply the union is connected, but y1 connected, y2 connected, intersection is non-empty will imply this is connected. Again this also we can prove that, suppose it has a separation y1, I mean just hint, y1 union y2, say it is A union B, where A and B non-empty open sets in the union y1 union y2, and we can prove that sets y1 y2 are connected subsets of X, that will imply they are also connected subsets of this subspace. So that means this will form a separation. Now y1 connected will imply y1 will be contained in A or B. Suppose y1 is contained in A, similarly y2 is contained in A or B, but it cannot happen that y1 is contained in A, mean we have a common point. Suppose if we take that point A, then that A will be in the, we will have this y1. So this it is in A and B. So I mean if y1 is subset of A and y2 subset of B, then we have a common point A, which is in A is in B. So that will give us A intersection B is empty. So but if you assume that it has a separation, separation means they are open sets such that this and A intersection B empty. So that will give us, we cannot have a separation. So that will imply this union will be connected. Exactly using the same idea, we can prove that each y alpha connected, intersection y alpha connected a family, then the union y alpha is also connected. Essentially you take a common element A. Now if this union y alpha has a separation, then all the each y alpha will be in either A or B. So that will imply we cannot have a separation. So that will give us this. Maybe in the next lecture we will prove the main results, namely the product of connected topological spaces is connected. That means each x alpha is connected, then the product space is also connected. I mean that is not easy to see that each, the R2 can be written as fix one line, this is connected, now all this vertical line union this one particular line, if we take that union you will get R2. So we will see in the next lecture. Thank you.